And I'm Jaya. Sorry. Hi. Uh, and this is a wonderful notebook that we at QSA Joe made to teach you more about quantum mechanics and introduce you to this wonderful field. So, before I start, I'd like to know, everybody here, um, what was your reason for doing quantum mechanics, or starting off with learn? What was your reason for learning quantum mechanics, or attempting to learn this exciting field of physics? uh, if you are comfortable to open up with your mic, or else you guys can put it down in the chat. Either. Um, Quantization of energy. Essentially, when what this means is energy is equivalent to h, your not your Planck's constant, times v, which is your frequency. And frequency is like, think of it out like the measure of how frequent your wave travels, of sense, because energy can be represented essentially, well, not necessarily energy, but it's more like, it's complicated, but v is the frequency of the quantum. So it's sort of like, well, all right. hmm And frequency is almost like your joules per second. In this case, it's energy, and h is your Planck's constant, which is joules per second, and frequency is in inverse seconds, which is 1/s, yeah, which would give you joules. Frequency is like how fast your wave's traveling. All right, you can scroll down now. Yeah, so the Bohr model of hydrogen. The Bohr model, a very outdated model. That's not actually how the actual hydrogen model looks, but this is a very good way to sort of understand it. We are usually in a physics class, we're known to know that energy is not discrete. Its energy is almost considered to be continuous. And you continuous in the sense that well, you might wonder what's the difference between continuous and discrete. Continuous is like, well, it just it's like a smooth flow. It just consistently flows. Where discrete's like, think of it like stairs. Like, when in this case, when you have an electron, the best way to look at it is, wait, I'd like to draw this picture myself and show it to you. I think I could share my screen. It would make it easier. Oh, paint, yes. I use this a lot. Okay, so you can think of this, not the best circle, but it works. Each of them has its own like electron energy. Sorry, electron levels. So orbit, yes. Well, not your orbitals, but your levels essentially, energy levels, and you have a bunch of electrons. You have a bunch of electrons everywhere. This is a random sort of particle I'm making. This isn't really. I don't even know if this is a real atom, but you don't have to worry about that. The point is, uh, you have a bunch of electrons. And when we mean energy is discrete, it means that there's like some exact amount of energy needed to make sure it rises to the next step, in the sense that it bounces this to be at this energy level, and then it bounces there to be another energy level. There's no in between. While like actual continuous like sort of energies, like the the best way to think about it is springs. Springs are gravitational potential energy. Gravitational potential energy just rises up with height, like a linear function. But here, there's just not that. It just bounces with responding to each energy level. And the coolest part is, energy is usually transmitted as a wave. is usually transmitted as a wave. Shorter waves have higher frequency. Thus, as we've learned in the equation hv, where v is frequency, having a shorter wave has more energy. Longer waves have less frequency, so having less energy, because h is just a constant. All right, moving on. You can share your screen again. Okay, awesome. Emission, absorption of light. Yes, same thing what I meant here. So you emit light when you're moving closer, you absorb light. Essentially, when you transfer from a higher energy level to a lower one, you're technically emitting it light. That's typically visible light. It's in all sorts of, because it's not necessarily light you emit here, you emit a wave almost. And that wave has a certain frequency that changes your sort of your different type of wave, well, sort of, well, different types. Like each wave has its own like microwaves, the different types of waves depending on the frequency of the wave. And when you absorb energy, you move up technically to high energy levels, because think of it like this. Your job is to try to get closer to the nucleus, and there's a ton of repulsion happening between levels. So you need more energy from your lower level to move up on the chain. Like I said, that ladder, it's discrete in essence. But there's only a specific amount of energy you need to move up. This energy can be heat, can be light, can be electricity. Yes, any sort of form of energy. But it's usually heat, light, or electricity. Or electromagnetic, which is light. Spectral lines. Yeah, lines are basically talking about your light, essentially. The sort of light that you emit. Each light has its own frequency. Each like sort of spectra has its own frequency, and that frequency matches up with the energy level the electron's moving. Ground state is it's more like it's its original state. Excited state, it's the state that it's not originally in, and at a higher energy level. What's next? Okay. Mm-hmm. All right. Wave particle duality. What this scientist Bruegel, just an old white dude, what he proposes is that every particle has an associated wavelength. And this is interesting because this also states that every particle also technically has energy, like it's just an intrinsic amount of energy, because we did define that energy is equal to Planck's constant times the frequency, and that frequency is associated with waves. So that means every particle has a sort of definite amount of energy given to it because of its sort of wavelength that was defined at the earlier notebook. So the way you'd calculate this wavelength is you take that thing means wavelength, the special symbol equals h, which is Planck's constant. We've seen that before, over p, momentum. And momentum is just mass times velocity, where mass is, well, the amount of matter you have. Velocity is like speed of the particle. And momentum is a vector, but don't worry about that here. We can move on. Particle-like properties. So, electrons have mass, they have a charge, and they have something, well, mass, everybody knows that. And charge is like sort of plus or minus, but it's considered technically in coulombs, and opposite charges attract, and same charges repel. And spin. This is the most, probably one of the hardest property. But what's happening here is the spin. And what spin is just angular momentum. An angular momentum of a particle. It's intrinsic, meaning that it's innate angular momentum. Spin is probably one of the most complicated parts of an electron. It's quite complicated to understand. Yeah. But Here, electrons can have two spin states, plus one half or negative one half, minus one half. And it basically determines how they behave in magnetic fields. Electrons with plus one half means they're aligning with the current magnetic field, and with minus one half, that means they would not both align against the magnetic field. And okay, so electrons are electrons get experiences by electrical fields. The experiences, so when they're placed inside an electrical field, they experience some sort of force, some forces, and these forces determine their motion, essentially. And wave particle duality. Electrons also are one of them that exhibit wave particle duality behavior, and that means they exhibit interference, and they also exhibit particle-like behaviors, which is, I assume, spin is a way of looking at it, because spin is angular momentum, wave particle duality. So you can see here that electrons are probably the best examples to show wave particle duality. For example, a we have angular momentum, which is definitely a property of a particle, and you have this interference patterns and diffraction patterns that are similar to waves. We'll get more into that later on this sort of lecture. So moving on, we can move back down. We can scroll down. Quantization of energy. We talked about it before. It just means there's stairs of energies. All right. So the double split experiments. This is one of the coolest experiments a physicist would love. Essentially, what happens is you have two slits, a barrier with two slits, and you send particles, electrons, and photons just going on, and they create this interference pattern. And this interference pattern, oh, you can move that. Yeah, exactly. When they move through, they create an interference pattern, as shown in that image. And that interference pattern tells you exactly where they hit. Because you would think if it was just a particle, the way it would work is it would just like be sent through those slits, and you'd never see those sort of the interference between each waves being affected. You just see them hit exactly between those two positions straight in a line. But that isn't the case. It shows here that they're they're demonstrating a wave-like behavior through that. And obviously you can see probably some particles that are in their particle form hit the other two walls, but most of them form this interference pattern. So you can move it. That thing's called the interference pattern, by the way. This is you can run the code, but it's probably running. So move down a bit. Yes. This is a heat map of the double split experiments. And, well, from the looks of it, it's talking about the accumulated impacts over the y position and x position. And the looks of it is it's obviously equally split up between two parts, the negative 1 point and the positive 1 point in x position. But you can see there's varying difference in impacts at each point. It's not an exact location it hits randomly. It's scattered around on the y-axis through the amount of impacts, or you can consider the amount of electron impacts, so particle impacts. Okay, we can move down. Yeah, this is a double split interference distribution. In essence, what it means is the electrons are just everywhere. Like, you can't predict where, but they're everywhere, essentially. As you can see, the wave is like sort of each, like all possible, like sort of field, not all possible, but sort of what we've seen in this pattern. This is the interference pattern right here. Where the mouse is going. That's the interference pattern, and this part of the experiment shows that. And this is a heat map of it. Heat map, as we can see, is just it's measuring the heat essentially. But here it's talking about the total accumulated impacts, which is pretty evenly distributed over, as you can see in the image. But here it's just complete like even distribution of particles hitting in those random positions. You can move down. Yeah, now we can go into this is the most important part of for not just quantum mechanics but also quantum computing. So pay attention. So classical versus quantum. All right. The biggest difference here is classical, they have definite, defined properties. You know where their positions are, you know what their velocity is, what their momentum is, you know everything about it. It's like you have control over a lot of variables. But quantum, it's complicated. Like there it could be it comes down to a certain, in this case we can talk about bits. They're the easiest way to explain it. In essence, a bit could be 0 1, but you can definitely control it, and it's only going to be 0 or 1, and you always know that. You can definitely, through multiple calculations, you can definitely figure it out. In quantum mechanics, though, you don't know that. It's just completely random in essence that it's going to be 0 or 1, but you don't know until you do something called measurement. And when you measure something, what happens is, you remember that wave interference pattern? Yeah, that thing collapses. The wave function collapses. And when the wave function collapses, the Schrodinger's wave function, but it's a really complicated wave function. Uh, but you just need to know it just produces a wave. And when that thing collapses, what it does is it converges at a single point, and that point is just the result. And that happens after a measurement. We don't know why exactly it collapses, but it just collapses, and that's just the property of measurement. When you measure something, it collapses at a point. Now, what's interesting is that if you consistently measure a particle without doing anything, it'll always, 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 after the first measurement, there's something important to learn about this, but after your first measurement, you don't know what's going to happen, and then you immediately know what's going to happen after that. Like you figured it out because you measured it. Now, if you measure like at some time frame, right, a couple minutes, maybe like a couple seconds after it, you would like a second measuring. That is going to be definitely at the same position because.
Wait, I'm sorry. I just had a quick question.
Yeah.
So I just got to the meeting. What are you covering right now? I'm sorry.
Oh, it's fine. We're talking about superposition. Um,
Oh, okay, I see.
do you know what that is? We're just starting off. It's
Yeah, I kind of know superposition. The
okay.
Planck's constant and stuff, right?
Sort of.
Okay.
We're gonna talk about it.
All right.
So actually, I was thinking maybe I could show you guys a drawing. Uh, I'm gonna share my screen now, just to yeah. A lot of the stuff goes into measurement to collapse, but
Wait, did you stop sharing your screen?
no, I'm just gonna share a new one.
Oh, okay. All right. Sorry, I got a little worried for a
And
second.
that's fine.
Thank you.
Yeah, we did. But we're just switching screens. Yeah. So what I mean is, think about it like this: you have a random wave function, right? And this is, let's say, position, right? Because everybody likes position. And this is, you can say, probability of x. P of x means probability. And your particle could be anywhere in this sort of deal. That's like a horrible sort of graph to look at, but let me try something a little bit more extreme. And it's not just here. I can show you a chemistry example later if you want. But yeah, this is a wave function. Yeah, some random wave function. The higher it is, the higher probability of it being here. So we can never exactly know where it's going to be, but then at some point after measurement, I'll just call measurement an operator here. Measurement. Okay, so I'm going to erase this. I hope you guys understand this. There's going to be some random function, and this is probability. The higher it is, the more likely it's going to be in this exact zone. And actually, I may have to change that, but that definition, it's the more highly likely it would be in at this position, x. And if you actually integrate this function, if you guys know what an integral is, what you'd actually get is it's between the probability a particle would be between this bound a and b when you integrate the wave function. But don't need to worry about that. We can talk about that later. This is just the introduction. But what happens is the graph sort of turns out to be like this after you measure it. And then you're like, oh, it's exactly here because you measured it, so you would know where it is. It's going to be exactly right here, just like flat out right there. And now it makes sense that after like maybe like a second, you might see the particle still here. It's kind of awkward, but it's still definite, but not indefinite. It just makes sense. After your first measurement, the second measurement, it's going to still be there. But then after some time, the function, like let's say you just forgot, you just left your like measurement device. I don't know why you do that, but you just left there to get Cheerios or something, because I like cherries. And what happens is that your wave function turns back into this thing. It goes back to this thing, and now what happens is you have to remeasure it, and you'll be in a completely different result. That's the point here. You get some random value that you can't predict. Oh, you can go back to sharing your screen. You can't predict. But unlike like something like a velocity versus time graph in realistic, like it all comes down to macroscopiness. But this is in a macroscopic point of view. You would exactly know at time t, a position versus time. Sorry, it's going to be exactly here, and that would never change. It would always be exactly there. Let's say we stop, we'll always be there. It's not like we're going to switch positions. We'll always be there. It's definite, and that's the point I want you guys to figure out at the end of this. That there's that classical is definite, quantum's indefinite. You wouldn't know. I might have to change that definition later on, but this is just the beginnings. Just think about it like that. Yeah, superpositions, examples. Yeah, these are a bunch of good ways of exempling superposition. Electron spin's one of them. It could be up or down until you measure it. And polarization. It depends on the direction, but until it's polarized, you don't know it. It can be in any direction. We can talk more about that later. But moving on, quantum interference. Oh, quantum interference, yes. This is basically saying when you have two quantum states interfering, here, this is probably best, I'm a visual learner, I'm probably sure, I don't know if everyone else is, but the best way to think about this is using a legit wave. Think about it like this. Let's say we're at like the ocean, right? And there's just a bunch of waves, this way, that way, that way. And now what happens is when they both interfere with each other, they both cancel out, and then you just get calm, regular water. But if they're both working together, and let's say it's just moving in one direction, you get a really ginormous wave. And if they're both working together in the other way, well, that doesn't mean they're interfering. But interference means that when two states are interfered with each other, what happens is this. They both like sort of cancel each other out and turn back to like a regular positional state, just whatever a regular value would be. Applications. Applications would be in QC, so we'll talk more about that later. Entanglement. Oh, okay. Entanglement. Actually, entanglement is sort of saying that you have two particles. You need two particles. That's necessary on this. You have two particles, particle A and particle B. You can assume they're circles, because I like circles. And entangle means they're connected. There's no actual line between them, but that's just it's metaphorically. They're connected together. And so you can think of it like this. When A has some sort of state, and some sort of like states are represented by this, a vector plus another vector. Actually, this is a state. Right here, that's one state. Right? We'd have to go more into vectors. Okay, I think we should start with that. Let's define how to define a quantum state. So, quantum states. They're going to work like this. You have O that and 1 this. The difference between these two are considered, this is called the 1 state. You can think of it as the actual 0 state, sorry. Oh, sorry. Okay. You guys can see my screen. Yes. I'd like some feedback, please. Okay. Moving on. All right, nice. So this is the 1 state, and this is the 0 state. Awesome. Two fundamental states. Think of it as just your qubits, 0 and 1, right? Everybody knows that. All right, so when something's in superposition, you have some P, I'll call it A because it's easier, plus B, 1. B and A, we're going to just consider the real number system here for simplicity. A is probability, and A squared plus B has to equal 1. The probability of, you have to square this value and square this value. And it'll always be 1 because probability of your sum of all probabilities is always just 1. It just doesn't make sense because think of it like this. I'm not sure if you know statistics or not, but I'd like to still. Your sum of all. Okay, never mind. I thought I saw something. Yes. Oh. Can you guys see my screen?
I think Taylor wants to ask something.
Oh, okay. Let's take a look. Who do you? Okay, do you guys can? Who wants to ask something? Any questions? I think I was moving too fast.
Nah, I misclicked.
Ah, okay, fine. All right. So now, sum of all probabilities x, right, is always 1. Fun fact. Oh, actually, we're going to talk more about quantum mechanics later. I want to hand off over here. We can stop here. We're going to go more in depth later, but this is enough for this current lecture. These are two states, 0 and 1. Abdullah, you can share screen now. And oh, sorry. Wait, I'll continue sharing mine. The thing is, this is considered superposition. Yeah, it's not that complicated, surprisingly. This thing is technically in superposition because until we're measuring it, until we're measuring it, we don't know which one it's going to be. It could be 0 or it could be 1 at the same time. The only thing we can guess is what is it going to be more likely. It could probably be 0 if a squared is larger than b squared, right? But their sum is always going to be 1 because it's the sum of all probabilities is 1 because let's say you have everything, and what's the probability of picking anything? It's always 1 because you'll always pick something. And that's superposition. I should have more reiterated it later, but now we're going to go into entanglement. Entanglement is essentially when you have two particles. Actually, yeah, when you have two particles, particle A and particle B. When their states are entangled with each other, it's like their fates are entwined. I don't even know if that's a real phrase, but their fates are intertwined. No matter the distance. This could be like infinity years away. That's not a real number, sorry. Light years away. The distance between them. Light years away. But they're still going to be entangled. What that means is this thing here and this thing here. And is that A has some sort of like sort of like, you can think of it like it's like since both states are entangled with each other, it has its own like set of probabilities, its own superposition. That's and this thing has its own superposition. And when this thing meets a certain superposition, that thing you know that it's going to meet. It's sort of split into two different superpositions. Like this could be a 0, 0, 1 plus b 0, 0, 0, 1 that, and this could be a 0, 0 means like first particle, second particle. A 0, well, sorry, 1, 0 plus b 0, 0. So if a is 0, if it ends up this probability a, right? If this is 0, then this must be 0. What that means is on this side, we know that this probability of b being this is this. It actually simplifies it. And it's not just that. When you collapse one, the other one technically collapses too. It collapses into this state when this collapses. And that's it. That's all what entanglement tells us. Any questions? All right, cool. So I think you can share your screen now. Thank you. Yep. Nice. Now we can go to known cloning theory. I would love to explain the linear algebra of this, but I don't know if all of you know this. So I'm not planning to actually talk about the linear algebra, but I'll tell you what this actual thing is. What this is that quantum cloning means that, let's say you have any random state, you have an arbitrary quantum state. It could be in superposition, it could not be. And most likely, let's assume it's in superposition. And we want to clone it, right? So the way you'd clone it. What that means is you want to make an exact copy of it through something called it's a unitary matrix, or it's a random function. Think of it like a function, right? You apply some random matrix or function here. Just think of it like a function to something, and it results in a copy. Basically, based on linear algebra, that's proven to be false, and that's not possible. That's an important thing. That's why it's called no cloning theorem. But I want to reiterate this. This is only not possible if and only if your states aren't orthogonal. And like, for example, you can clone a zero state, right? That's obvious. You can clone a zero state because it's orthogonal, and it's obviously inner product. Okay, I can't explain that. That would go into more and more vector math. So you can clone orthogonal vectors, but you cannot clone two vectors. You cannot clone when one of these states aren't orthogonal to another state, because it's just impossible. Like, it just doesn't make sense. It's just impossible to predict that. It actually causes lots of probabilities that can't be distinguishable between that and another bit, because those two because one is dependent on some sort of varying probability. It could be anything. It could be that or that. You can't just distinguish them because they could both be the same thing. It's hard to distinguish between them. But if they're orthogonal, it is really easy to distinguish between them because one is going to be perpendicular to the other. So, what does orthogonal mean? All right, awesome. That's a great question. So orthogonal means perpendicular. That's all it means, perpendicular. I would say the inner product equals 0. That's the real definition, but if you look at it graphically, it just means perpendicular. Sorry. Yeah, perpendicular. When two vectors are perpendicular to each other. Think about two lines are perpendicular. So, nice. Now, implications. How this is important. What this means is that it's more into quantum encryption, but if anybody wants to eavesdrop or sort of like look into eavesdrop, I guess everyone knows what that means, but on a communication channel, then this thing, when you copy it, it would technically, well, what would happen is, would essentially would disturb your quantum states. Like, because when you're eavesdropping, you're sort of measuring it, and when you measure something, it gets affected. There's more error, and when you can use this, so no cloning theorem is helpful because now you can't really actually clone sort of your states. Because if someone could clone it and listen to it, that'd be broken. Yeah, that would just break the system. So now moving on, quantum teleportation. Um, they know you're not teleporting from one place to another. It's not as cool as that yet. But what happens is you essentially transfer a bit of quantum information from one channel to another sort of channel, like by actually physically moving the particles. Because quantum computers, before we continue, I want you guys to understand this, that quantum computers, all they are is actual just physical particles. Like, you can't really use like technical like structures. You have to come up with something unique. Wait, we're gonna talk about qubit modalities later, but some of them are based on ions, some of them are superconductors. I'm probably sure every single one of you guys have heard what a superconductor is. But room temperature superconductor. I don't know how true that is, but moving on. Yes. Okay. Well, bell measurement. The way you do a bell. Well, that goes into quantum computing. I think we'll talk more about that later because all of this is quantum computing, and we're going to discuss about that next lecture. We can move on. Oh, this is it. Any questions? Any questions? We could. Also, I'd like to point something out, guys. I know you're really busy, and I would really love them to have a book club where we just discuss about quantum mechanics, because one of the best ways to learn quantum mechanics is discussing more in depth. What we're doing right now is just an overview. So if anyone would like to join, that would be awesome, and we could teach more about quantum mechanics. And if you really liked if you really like the taste today, the taste of quantum mechanics, I sure hope you guys can join us next time. Like, we're learning more quantum. I hope to make this a weekly session.